Hello students, in the previous class we discussed about different type of magnetisms, what are the basic terms involved in magnetism. Today we will discuss about the diamagnetism and we will describe what is the classical theory of diamagnetism, which is also called the Langevin's classical theory. As we discussed earlier, the diamagnetism in a material arises due to the changes in the atomic orbital states which is induced by the applied magnetic field. So an electron which is revolving in an orbit about the nucleus of an atom is equivalent to current and which has got a magnetic moment. And if the orientation of the electronic orbit is such that the vector sum of the magnetic moment is zero, then the atom as a whole has no resultant magnetic moment. But when we applied an external magnetic field, the velocity of electrons is changed and a magnetic moment can develop in a direction which opposes the applied field. So this is in accordance with Lenz's law. So when a magnetic flux linked with such an electric circuit, so this is analog to an electric circuit, is changed, an induced current can be set up in such a direction that which oppose the changes in flux. The induced field will be always in opposite with the applied field. Almost all material shows the diamagnetism, but as we discussed earlier, the effect of this one is very small. The susceptibility, the magnetic susceptibility is defined as the magnetization induced by unit field, which is very small value. It is only of the order of 10 raised to minus 6. So it will be suppressed. This effect will be suppressed by strong field effects such as the ferromagnetism or paramagnetism. In order to describe the classical theory of diamagnetisms, consider an electron revolving around the nucleus in a circular orbit with frequency omega 0. So that is the original frequency. The basic of this theory is that the change happenings to the magnetic flux, which is the changes in current, can be manifested by changes in the frequency of revolution of the electrons. So we consider omega 0, which is the original frequency of revolution of electrons in the absence of the magnetic field. But when we apply the field, this frequency will be changed. So the effect of the field can be studied by the changes in frequency of the revolution of the electrons. The changes in the current in the presence of the applied field is manifested by the changes in frequency of revolution of the electrons. And if omega 0 is the frequency of revolution of electron in the absence of the applied field, and let rho be the radius of the orbit, as we seen here, rho is the radius of the orbit, v is the velocity. So v is the velocity of linear velocity of the revolution of this electron. Then we can equate this equation as m omega 0 square rho is equal to z square by 4 pi epsilon naught into rho square. The left hand side of this equation is the centripetal force, that is that we can write as m v square divided by r. This is the general equation for the centripetal force. Here where v is the linear velocity and it is related to the angular velocity as v is equal to r omega, but in this case r is equal to rho, that is the radius. So this is v is equal to rho omega, and this r is rho, this r is also rho, so that this centripetal force equation becomes v is equal to rho omega 0. This is rho omega 0. This is the frequency in absence of the field. So this equation become m omega 0 square rho is equal to, this is the electrostatic force of attraction between a single electron orbiting around the nucleus and the center of the nucleus. So that is 1 by 4 pi epsilon naught into q1 q2 by r square. Here also instead of r we use rho. So this equation become like this. From this equation we can obtain the expression for omega 0, that is square root of z square by 4 pi epsilon naught into m rho cube. In the presence of a magnetic field induction, the Lorentz force of an electron moving around the moving with a velocity v is given as F is equal to q v cross b, Here Q is E, that is the charge of the electron, V is the velocity, and B is the applied field. So this equation will be EV B into sine theta. Assume that the field is perpendicular to the orbit. So this electron is orbiting around nucleus, and this field is applied, and this is the velocity at which it is moving. And if this field is applied perpendicular to this plane, then these two are perpendicular to each other, so that the sine theta becomes 1, and we will get obtain the expression for force is equal to E rho omega into B. So that is in the presence of the applied field. So instead of omega 0, we have to use omega, that is the frequency of electrons in the presence of applied field. Here also we substitute V is equal to, here the V is rho omega, that is R omega is become V is equal to rho omega, where rho is the radius of the revolution of the electron around the nucleus. According to Lenz's law, the applied field have an opposite effect. So this will oppose the original force. So the new force equation can be m omega square rho is equal to, this is the expression m omega 0 square rho minus E rho omega into B. So this is this term has came in the presence of the applied field, that has got a opposite effect. That's why we use minus sign here. So this equation can be simplified as this one can be simplified in this format, that is omega square plus EB by m into omega minus omega 0 square is equal to 0. So this is these expressions, these two terms, we equate these two terms. Now this equation can be simplified. This is a quadratic equations, and the solution of this equation is in the form of minus b plus or minus square root of b square minus 4ac by 2a, that is 2. So this equation become 1 by 2 into minus eb by m plus or minus square root of eb by m all square plus 4 omega 0 square, because already there is a minus sign. And we can further simplify this equation, so you will get omega is equal to plus or minus square root of omega 0 square plus EB by m all square minus EB by 2m. Suppose the value of EB by m, EB by 2m is much smaller than omega 0. This field is, we can consider that the effect of field is not very significant. So that case, this equation can be, this term can be neglected. The second term of this equation can be neglected. So finally, we get the expression for omega, which is closely equal to plus or minus omega 0 minus EB by 2m. So that is the new frequency. So on the application of the applied field, the new frequency of revolution becomes plus or minus omega 0 minus EB by 2m. So this is the Larmor's theorem, which proposed that the only effect of a weak magnetic field B is to cause the entire motion to precess around B by a frequency value of EB by 2m. So that is the effect of an applied field. It will have a frequency change which reduce the frequency by a factor of EB by 2m. The electrons with orbital moments parallel to the field will be slowed down, whereas those with moments anti-parallel to the field will be speeded up. Now we understood that there is a changing frequency due to the applied field. So this changing frequency can produce an additional current, which is given as I is equal to charge into revolutions per unit time. So this is actually the frequency nu. So this is the frequency nu. You know that the angular frequency omega is related as 2 pi nu, which is the this nu is the revolutions per unit time, 1 by period. So this is the charge of the electrons. Remember that in this case we only consider one single electron revolving around the nucleus. So that's why we need to use only minus E. Otherwise, if there are set number of electrons, we have to substitute for Z into E instead of this. So this one charge into that is, this is the omega, that is the additional frequency term EB by 2m by 2 pi. So that gives the current produced due to this changing frequency. So this expression is E square B by 4 pi m. So there is a negative sign. Correspondingly, this current can cause a magnetic moment. The magnetic moment mu of a current loop is given by the product of the current and area of the loop. So in this case, you remember we consider a electron revolving in a closely circular loop. So if you want to know what is the magnetic moment of the current loop, we need this will be the current times the area enclosed by this one. So that is I into this expressions, that is this I into this area. So area of the circular loop is, that is pi r square. So that is the area. So here the radius is rho. So this expression becomes the minus E square B by 4m into rho square, which is the expression for the magnetic moment. Here there is a negative sign which indicates that the induced magnetic moment point in a direction which is opposite to the applied field. In the previous case, we considered two assumptions. One was the applied field is perpendicular to the plane of the orbit. Also, we consider only a single electron which is revolving around the orbit. But in a real case, B may not be perpendicular to the orbit. Also, if the atom containing Z number of electrons with their orbits randomly oriented, then the total induced magnetic moment will be, so we need to consider Z in terms instead of E, we need to multiply that charge with Z. So this will be Z E square B by 4m. Also, since these electrons are revolving in random orbit, we need to use the expectation value of rho square. And if the field points are along the Z axis, this rho square will be is equal to the expectation value of S square plus Y square, which is the mean of the square of perpendicular distance of electrons from the axis of the field. Now the mean square distance of the electrons from the nucleus is given as more or less this one, expectation of R square is equal to X square plus Y square plus Z square. So in the previous case, we consider electrons are revolving about an axis with a radius rho. But now we are considering the mean square distance from the center of the nucleus. So that value will be X square plus Y square plus Z square. And we consider the spherically symmetric charge distributions. This X square should be equal to Y square, should be also equal to Z square. Since we consider that the rho square in the previous slide, rho square is equal to X square plus Y square. So the expectation of R square will be 3 by 2 into rho square. Since X square plus Y square is rho square, also this is also equal to Z square. We are adding 1 by 2 into rho square 3 times. So that is 3 by 2 rho square. Now the total induced magnetic moment, which will be equal to Z E square B by 4m into 2 by 3 expectation value of R square, which is equal to minus mu 0 Z E square X by 6m into R square. Now if you are considering a solid which consisting of n atoms per unit volume, each containing Z electrons, magnetization is defined as the total magnetic moment per unit volume. So that is n into in this case the magnetization will be m is equal to n times mu a, where n is the number of atoms per unit volume and mu a is the total induced moment of the atoms. So now if you want to consider the susceptibility, that is the magnetization produced with unit field. So that is susceptibility psi is defined as magnetization per unit field, that is equal to, we just divide this one with the applied field H. The expression of the susceptibility will be n mu 0 Z E square by 6m into expectation of R square. Finally, we arrived at the expression for magnetic susceptibility of a diatomic material, which is given as psi diatomic is equal to minus n mu 0 Z E square by 6m into R square. So this expression is known as the classical Langevin's result for the diamagnetic susceptibility. From this expression, we can arrive at following conclusions. That is, the diamagnetic susceptibility is a negative and is independent of temperature and intensity of magnetic field. So the quantity is a negative quantity, which implies that it is just opposite to the applied field and is independent of temperature. If other susceptibility values such as paramagnetic or ferromagnetic values, which will be depending on temperature, which is inversely depending on temperature, but this term is independent of temperature. And also there is a term Z here, so that means for large number of atoms, if there are large number of atoms, the atomic number will be larger, so the susceptibility value will be higher. For such atoms, the susceptibility value also will be higher since it is proportional. For most of the material, this susceptibility value of diamagnetic material is only of the order of 10 raised to minus 6, and this is relatively very small effect. So if you compare with other susceptibility values, this is relatively small value. It is only of the order of 10 raised to minus 6. So it will be suppressed by other magnetic effects. And if you have any doubts on this material, please contact me. Okay, thank you.